Hello, everybody. This is Coach Mindbauer here for AP Calculus. This is for AB and BC. We're going to talk about limits at infinity. This can be a loaded topic here. A lot going on, a lot of stuff. So let's just dive right into it. A couple of basic limits that you do need to know are the limits as we go out to infinity for 1 over x. That's equal to 0. That is because we can sketch this and graph. We have asymptotes at the axes. If you notice, the right end behavior goes to 0 and the left end behavior also goes to 0. That's why we just lump them together. This next one, though, this limit one, maybe I can remind you what some stuff we did in Algebra 2. You probably saw this before. We have rate over the number of times as a ratio in this. So it's p times 1 plus r over n, all to the nt. That is when we do compounding growth, or it could be compound decay, depending if r is positive or not. And we taught you compounded continuously. That's when n is infinite, and we would get that as a equals p e to the rt. It's the same idea. If we're compounding this n to the infinite, you end up getting e. So like another way I'm going to write this out is going to be the limit as x goes to, and this works for the right and the left end behavior, so I'll just lump them together, of 1 plus a over x to the bx is equal e to the ab. Just like on this compounded continuously, we have the r and the n, the r and the t are represented as my a and my b. So if you can draw that conclusion, it's great. If not, just memorize it. And then we have arctan, and this is going to be a function that has 2 horizontal asymptotes. One is going to be up here at pi over 2. One's going to be down here at negative pi over 2. And it looks like this. So that's how we get those limits right there. Some definitions here. I hate how this is written. So if we can just add f of x's in all of these, because this is proper notation then. Bugs me a little bit. But essentially, to prove a vertical asymptote, which is something you should have done in pre-calculus, to prove a vertical asymptote, which is this top one here, you just need one direction to give you either positive or negative infinity. You do not need to prove both sides. Just proving one side is enough. And for horizontal, same thing. You just need to prove one side if it equals a. But sometimes it's worth checking to go to negative infinity just in case there is a second horizontal asymptote. Limits of ratios of 2 functions can be is written as limit as x goes to infinity or negative infinity of g of x over f of x. If the f grows faster, which is what it says right here, if f grows faster, if it's faster on the bottom, we're going to equal 0. If it's faster on top, we'll be either plus or minus infinity. Here is our order of operations here. Now, there's a lot going on. Just assume that a, c, and d are all equal to or larger than 1. And so all you need to know is just the ln's grow the slowest, then the polynomials, then the polynomials times the ln's, and then the polynomials that are compounded on it. So if you do a polynomial times a polynomial, and then the exponential, then the factorial, then the x to the x. Okay. So let's go ahead and look at this. Oh, this looks like this is written poorly. I will have to... It is not written this way in the notes, so let me just go ahead and finish this up. This should be a square root. And this should be a square root. For some reason, the square root's kind of sort of got cut off there. What I'm going to do is I'm actually going to start and snake around here. I'm going to go a little bit different of an order. I'm going to start over here. If we're ever looking at end behavior within a ratio, you just want to find what's going to change the most. So in other words, what is growing the fastest for each term. So if you look at this one for 3x plus 5 over 6x minus 8, which term grows the fastest on the top? We're going to find out that the 3x is going to grow the fastest. On the bottom, the 6x is going to grow the fastest. So that's all I care about is just fight between the 3x and the 6x. And that actually will simplify easily because the x's will cancel out. I'm going to get 3/6, which is 1/2. Okay. I do want to add another problem here real quick, just so you're kind of aware. Let's go to positive infinity for this one. What if I had 2e to the x minus 5 over e to the x plus 1? Like, what if I had to solve that one? Well, look at the highest powers. The power that grows the fastest as we go out to infinity is going to be the e to the 2e to the x is the fastest one. And then the bottom, we're just going to get e to the x. This is going to give me an answer of 2. So we're going to have a horizontal asymptote at 2. Also, let's investigate if we go to negative infinity of 2e to the x minus 5 over e to the x plus 1. Now this one, which one grows fastest? Now the rate of change of e to the x as we get further and further left is it's gonna approach 0. So as we actually plug in a really, really, really large negative number, if that makes sense, like negative billion, negative trillion, that's gonna knock out the first term, and that negative 5 is still gonna be standing there. So we're gonna say that as we go to negative infinity, this is gonna be negative 5 over 1. Okay, why is that true? Well, the graph of an exponential has a horizontal line at y equals 0. So as we go further left, we're approaching 0. Okay, that's not the case here for this example, this 3x plus 5 over 6x minus 8. If we did go to negative infinity, we would get the same answer because the x's are still changing at negative infinity, just like they are changing at infinity. Sliding on over, this is just like that formula we went on the front side. So here I can rewrite this little part right here as 1 plus 1/2 over x to the x. So our a term is 1/2. Our b term is 1. So this is going to equal a or e to the 1/2. This one right here, on my old notes, this is written together, but I think it's easier if it's separate. And you'll kind of see I'll do the same thing over and over again here. So as we go out to infinity for this one, I'm going to look at what's growing the fastest on the top. And I want to include that square root. So I'm going to get square root of x squared. Growing the fastest on the bottom is just 3x. It's really important to note that the square root of x squared is equivalent to absolute value of x. You do need to know that. So I can easily rewrite this as the limit as x goes to infinity of the absolute value of x over 3x. Now, it's important to know what absolute value of x looks like. It looks like a v, like this. And we should also know by definition, sorry, this is not writing correctly. We're at positive x when x is greater than 0, and we are at negative x when x is less than 0. So since we're going to positive infinity here, this is equivalent to x over 3x, which gives me a 1/3. Okay. Now I'm going to do the same thing here for the negative infinity. Really, I can do the exact same steps. And I can get down to this. X approaches negative infinity. So same steps. I'm going to be left with absolute value of x over 3x. What's important for this one to note is that since we're going to negative infinity, if I come back up here and show my definition, as I go to negative infinity, x is less than 0. So we're going to use the negative x version of this. Sorry, my Cami is deciding not to work very well, so this handwriting is going to get worse. But you know what? We're all going to put up with it. So this is going to give me an answer of negative 1/3. Okay. For this example down here, this is just the growth. Which one grows faster? 2 to the x or 2 factorial, x factorial. If you look right here, the exponential grows slower than the factorial. So we're going to grow fast. So this grows faster. So this is going to equal 0. Almost done here. We're going to find vertical asymptotes using the definition. So definition from the previous page was just saying when you find the vertical asymptotes, we got to make sure that the one-sided limits do get us to infinity or negative infinity. You can look at this upon inspection. You can factor this, and you can clearly see that this is equal to x plus 2 all over x minus 1, x plus 1. And you can clearly tell we have vertical asymptotes at -1 and +1. Now, I do want to get this checked by using a definition. So the definition is up here on the top there. We just need to take these a values and just show one or the other to the right or to the left. So I want to show that the limit as x approaches -1. You can pick the right or the left. It does not matter. Just for giggles, I'll pick left of this function, x squared plus 2x all over x squared minus 1. Now, it's super easy to make a number line for this one, since this is a rational function, polynomial on top and bottom, to see when this function is positive and negative, because I know this goes to either infinity or negative infinity, because I'm going to get the form of number over 0. So if I make a number line here for this f of x, I have that, just set every single factor right above that equal to 0. So I have a 0. I have a -2, I have a -1, and then I have a 1. Okay. Since every x is positive, our end behavior on the right-hand side is positive. And at the factor at 1, the x minus 1 has a power 1. So every odd power is going to cross the x-axis. So we switch signs there. That x is to the 1 power, so we're going to change signs again. The x plus 1 is at a 1 power, so it's going to change signs again. And then at the x plus 2, it's a power 1, it's going to change signs again. Now, what if we had purple? What if that was an x squared? Then we would actually not change signs here at 0, and then everything else would change. Okay, so that was a what if. Let me erase that what if. Okay, now we can just go ahead and use that sign chart and look. If we look at -1, what's going on left of -1? We're going to get, I want this in blue. We're going to get negative infinity, because we know it had to be an infinity. And if we look left of, on that sign chart, left of -1, we're going to be negative infinity. So that proves that we have a vertical asymptote at -1. If I want to look at, oh no, not -1. I don't need to check -1 to the right, by the way. Once 1 works, we're good. Let's go ahead and check 1. You can pick the right or left. I don't really care. I'll pick the right. Look at 1 to the right of this on my sign chart. You can clearly tell that we're going to positive infinity. So that clears and says that, hey, this is the proof of saying that we have vertical asymptotes at x equals plus and minus 1. Okay. Limit as x approaches infinity of sine of x. Sine of x, by the way, looks like this. It's periodic. Maybe I didn't draw that absolutely perfect, but it's going to keep changing signs up and down as we go through. So it has no end behavior. So we're going to say that sine does not exist as we go to infinity, because sine of x oscillates at its end behavior. Last one. This is a composition function one. That if it's not in your notes, I want you to add it in right now. So hit pause, add it in. Okay, so we actually have two functions here. If I were to say that we have f of g of x is equal to e to the cotangent of x. Okay, the inside function of this, g of x, is cotangent of x. So the exponent. The outside function, not just e, it needs to be a function. So let's do e to the x. So if we were to plug in g into f, that's what we would get. That's going to help us out a lot here, because since this is a weird one, so I first want to, kind of going in my order of operations here, I want to find out the limit of the inner one first. So what's going on at cotangent of x? And then once I find that out, I'm going to find the limit as x approaches that answer of e to the x. So pretty much whatever I get here I'm going to plug into here as a composition, and then that will give me my final answer. So that's what I want to happen here. So let's find out what goes on at cotangent. Now, it's really nice to know what cotangent looks like. If you don't know, cotangent is just cosine over sine. So we have vertical asymptotes at whenever sine is equal to 0. And that's going to happen at pi over 2. It's going to happen here at 0. It's going to happen here again at negative pi over 2. Okay, and it's actually a decreasing function, so it looks like this. This is a good reason to brush up on your pre-calculus because you're going to need to know this. We actually have zeros here at, actually, no, I have this wrong. It should be pi. Oh, no, I'm not redoing the video. These are pi's. Yeah, hold on. I got to think real quick. When is sine equal to 0? At 0 and pi. Yeah, these are pi's. Good thing I kept you on your toes, right? I'm just trying to see if you're paying attention. These zeros are at pi over 2. Apologize, I'm going really fast. Anyway, if we look at this graph right here, what's going on just right of 0 for cotangent? We're going to infinity. So I'm going to take that value, plug it down here. So now I want to see what's going on. So with e to the x. So as we approach e to the x, as we go to infinity, and I drew that earlier, I'll label this as cotangent of x. E to the x looks like this. So as we go to the right, that also equals infinity. So what that means is this answer is equal to infinity. All right, and that is going to wrap up our notes here for limits at infinity. Sorry, it's a long video, but this is all really, really good stuff to kind of get us propelled into calculus. So thank you. Please like and subscribe.